morning. Today we'll see about the direction coupler and its scattering parameters. So direction coupler, it is also a 4-port network. So this port 1 and port 2 is the main arm, or we can say this is a primary guide, and this port 4 and port 3 is your auxiliary arm or secondary guide. Okay, so in this port 1 and port 2 is a collinear arm, and port 4 is the forward port, and port 3 we can terminate. Okay, it is always terminated. So anyone in this secondary waveguide, any one of the port is always terminated. So here let us assume, for our clarification, let us assume that your port 3 is always terminated. Okay, this port 4, it is the coupled port. Right. So your direction coupler, it is used for measuring your impedance measurement. It can also be used to measure your power, your reflected power, VSWR values, and all those things. Okay. Right. So your PI, that is a P port 1, it is called as the incident port, and port 2 it is called as the received port, and port 4, because we have a forward coupling, so this is called as a coupled port or a forward coupled port. And port 3, it is called as a reverse coupled port. Otherwise we can even tell it as a back power, this back power port. Okay, so PI is my incident power, which is being given at port 1, and PR is my received power, which is seen at your port 2, and PF is your forward power, which is seen at your coupled port, and PB is your back power, which is seen on the reverse coupled port. Okay, so when power travels from port 1 to port 2, some amount of the power will be coupled to this port 4, but it is not coupled to port 3. Okay, same way when you give, because this is a bidirectional, it can also be as a bidirectional. So if we give power at port 2, we'll get at port 1, and some amount of the power will be coupled to port 3, but not to port 4. Okay, and suppose if the power is incident at port 3, let us assume like this. If the power is incident at port 3, your portion of power will be coupled to port 2, but not to port 1. The same way, if we give input at port 4, it is coupled to port 1 and not to port 2. Right? So we can simply say that P1 and P3, okay, the port 1 and port 3 is decoupled. Same way, your port 2 and port 4 is decoupled. If I give at 2, I will not get at 4. If I give input at 1, I will not get at 3. Right? So your 2 and 4 is decoupled. Same way, your 1 and 3 is decoupled. And for your directional coupler, to say or to determine a good direction coupler, we need to see some following parameters. So those parameters are your coupling factor and your directivity. So coupling factor, it is actually the ratio of incident power to the forward power. So where was your incident power? At port 1, right? At port 1 was your incident power, and at port 4 was your forward power. Same way, your directivity, it is the ratio of forward power to the back power. So forward power, it has port 3, and back power, sorry, 4, and back power is at port 3. Okay. So it is the ratio of incident power to the forward power. Okay. So my incident power is at port 1, and my forward power is at port 4. Okay, same way your directivity, it is the ratio of forward power to the back power. So forward power, it has port 4, and your back power is at port 3. Okay, and also we have one more parameter to measure, which is your isolation loss. So isolation loss, it is the ratio of incident power to the back power. So what is incident power? It is PI, isolation, So isolation power or isolation loss, it is the ratio of incident power to the back power. So we can write like 10 log incident power to the back power. So it is Pi to Pp, or I can say it is a ratio between Pi means P1, Pb means P3. So how can I write this? I can write like a P1 P4 into P4 P3. So this 4 will get cancelled and I'll get P1 P3. So this is your coupling factor and this is my directivity. So my isolation is coupling plus my directivity. Okay. So coming to the types of directional coupler, we have like single hole directional coupler, two hole directional coupler, multi hole directional coupler, okay, dual directional coupler, bidirectional coupler, hybrid coupler. So these are all the different types of couplers, directional couplers. And in your two hole directional coupler, the spacing between two hole is 2n plus 1 into lambda by 4. Okay, so this is the spacing. And okay, let us come to the matrix, directional coupler matrix. Okay, so for your directional coupler, we have 4-port network. So we can say it is a 4 cross 4 network, 4 cross 4 network. And if your directional coupler, all the 4 ports are completely matched, perfectly matched, then I can say my SII equal to 0, right? So here I'm telling all the 4 ports are completely matched. So S11 equal to S22 equal to S33 equal to S44 equal to 0. And we also see, we have also seen that in the property that your port 1 and 3 is decoupled, same way port 2 and port 4 is decoupled. So S13 and S31 equal to S24 and S42 is 0 because of the decoupling. And if I substitute all those things in your matrix 4 cross 4 matrix, I can get like this. So this is S12, S14, S21, 23. So these are the components to be measured now. So what is the next property? I can say my if I multiply with your complex conjugate, it should be equal to unit matrix, right? So 1 second. So see here. So since it is a 4 cross 4 matrix, we have these parameters, 16 parameters, and since all ports are perfectly matched, so S11 equal to S22 equal to S33 equal to S44 is 0, and since it is having a symmetry property, you can write like S12 is equal to S21, all those things. And because there is no back power, I can even say PB is 0. So there is no coupling between P1 and P3 and P2 and P4. Okay, so this is actually P4. Okay, so this is P2 and P4. Okay, no coupling between P1 and 3 and P2 and P4. So if I substitute all those values, finally I get my matrix as this. Okay, so now what is the next property? If it is multiplied with complex conjugate, I can equate it to identity matrix. So I'm equating it to an identity matrix. Now then I'll find out what is my row 1, column 1, row 2, column 2 and all those things. So if it is same row, same column, I have to equate it to 1. If it is different row, different column, I have to equate it to 0. So this is the conditions. So now from 1 and 2, I can write S14 is equal to S23. Same way from 2 and 3, I can write S12 is equal to S34. So this condition. Okay. So in this, let us assume that my S12 is a positive component. Okay, S12 is a positive component. So S12 is a positive component means S34 is also a positive component. So if I'm substituting that in this equation 5, so I can write like S12 is positive component P and S23 plus S14 into a positive component P. So I'm taking this P commonly out. So I can write P into S23 star plus S14 equal to 0. Here my P is always not equal to 0. So definitely this should be equal to 0. So I can say S23 is a imaginary. That actually that should be the imaginary part. And P is not an imaginary, then this should be definitely an imaginary part. Okay, so I can write my S23 as JQ. Because I also know that P square plus Q square is equal to 1. Because of this condition, I can write like S23 and S14 is a JQ. So substituting that in the value, so this is my matrix. So wherever I have S12, I can substitute as P. Wherever I have S34, I am substituting the positive terminal. And the imaginary value S23 and S14, it is an imaginary value, so I am substituting. So this is the scattering matrix for the directional coupler.